Welcome to the closing keynote of the conf, to SIG scheduling deep dive, actually. So my name is Salamat. I work at Google. I am the lead, or one of the two leads of SIG scheduling. Before Kubernetes, I used to work on Borg. And about 2 years ago, I started working on Kubernetes, and I've been leading SIG scheduling for the past 1 year or so. So most of these deep dives are meant to be like Q&A. As a result, I didn't add a lot of slides to my deck, so I'm going to go through them, hopefully in about half of the time slot that we have, and then we'll open up to questions that you may have. To get us started, I would like to very quickly tell you what Kubernetes Scheduler is. So basically, Kubernetes Scheduler is a component in Kubernetes ecosystem that is responsible for finding nodes for running pods in the cluster. Kubernetes Scheduler, unlike some other cluster management networks or cluster management systems, is not responsible for life cycle management of pods. It never creates any pods, and it kills pod in very few circumstances. Actually, this is kind of a new feature in Kubernetes, which is essentially preemption. I'm going to talk about that a little bit later. Kubernetes Scheduler is a feature-rich scheduler. It supports many features. Among the notable ones, I can point out node resource checks when it schedules pods. It has the capability of spreading pods of a collection among nodes of a cluster. For example, if you have a replica set, it puts replicas of a replica set in different nodes or in different failure domains, such as zones, regions, etc. It supports taints and toleration. If you're not familiar with these, taints and toleration is a feature in Kubernetes where you can label some of the nodes with a special label, let's say, which is called taint. And those taints cause pods to not get scheduled on those nodes unless they have a corresponding toleration for those taints. It supports node affinity. Basically, you can, in your pod spec, you can specify what kind of nodes or what specific nodes in the cluster you want this pod to be scheduled on. It supports interpod affinity, which essentially means where you want your pods to be scheduled close to some other pods in the cluster. This is useful, for example, in case you want to run, let's say, a cache server next to a web server and stuff like that. Also, similar to interpod affinity, it supports interpod anti-affinity. Anti-affinity is useful for a case that, for example, you don't want to run two pods next to one another. Let's say you don't want to run multiple web servers on the same node. You can do that by having anti-affinity. Kubernetes Scheduler supports checking node conditions. In Kubernetes, nodes can have certain conditions. For example, if a node is under memory pressure, it gets this memory pressure condition. Or if there is a PID pressure, it gets that condition. So the scheduler tries to avoid those nodes which have issues or are under certain restrictions. Other than some of these sort of like filters, Kubernetes Scheduler has some preference as well that sometimes in the code we call them priority functions. Basically, these are preferences for scheduling. For example, Kubernetes Scheduler can prefer choosing nodes which have lower resource utilization or high resource utilization, depending on the config that you give to the scheduler. This is useful for the case, for example, if you want to spread your pods among different nodes in the cluster to achieve higher availability, you can specify, like, choose nodes with lower resource utilization. Or if you want to reduce the cost, you don't care as much about availability, you can ask the scheduler to put as many pods as possible on fewer nodes. So in that case, you want to use, like, choose nodes with highest resource utilization. You also have a number of other preference. For example, the scheduler can put your pods on nodes that already have images that those pods require to reduce the amount of network usage in your cluster. So with that, I'm going to talk about what are the recent developments in the world of scheduling in Kubernetes. One of the areas of our focus have been performance. So we wanted to improve performance of the scheduler. As a part of that effort, and other than some of these algorithmic improvements, we have done, we've added a new feature to the Kubernetes scheduler that we never had before. Borg and many other similar schedulers usually had this feature where once the scheduler finds a certain number of nodes feasible in the cluster, it picks one of those nodes and doesn't continue scanning all the nodes in the cluster. But Kubernetes scheduler didn't have this feature. Basically, let's say in a 5,000 node cluster, it would scan all the nodes for every single pod all the time. And as a result, of course, performance would drop. But in large clusters, like a cluster of 5,000 nodes, we don't really need to scan all the nodes every time. For example, the scheduler can say, OK, I have already found 500 feasible nodes. Let's pick one of them and move on. So this feature basically helps you configure that. So there is a flag or a configuration parameter that you can specify what percentage of the nodes the scheduler should find before it stops looking for more. As you can see here, this has a relatively significant performance impact. If you scan all the nodes in a cluster on the very left side of this graph, you see that the throughput of the scheduler is in a 5,000 node cluster is about 35 pods per second. But as you reduce this percentage all the way to like 5%, it can reach to 90 pods, over the 91 pods per second. 5% in a 5,000 node cluster is still significant. So basically, it stops scanning for more nodes once it finds 250 pods in that cluster. By default, this flag is set to 50% basically, which is still high. In large clusters, it's still very high. But you can modify that if you run large deployments. We also have a plan to make this semi-automatic. Basically, you can still specify it if you want, but based on the cluster size, it's automatically adjusted in the next version or maybe the version after that. Another area that really required performance improvement is interpod affinity and anti-affinity. All of those folks who have tried to schedule Kubernetes in the past and have used interpod affinity know that it was a very, very slow feature. Actually, it was like 3 orders of magnitude slower than other features, other scheduling features. So it was so bad that we had to go and mention in the documents that don't use this feature if you run any cluster of more than a couple hundred nodes or so. But we've had a kind of a breakthrough in improving performance of this feature. And from like 600 milliseconds for a single pod in a 1,000 node cluster, we reduced the time to 5 milliseconds. So it's about 120x performance improvement. So you can now actually use this feature more or less similar to any other scheduling feature. It's still slower, about like maybe 8 times slower than other features, but it's no longer like 3 orders of magnitude slower. So it's usable in clusters of multiple thousands of nodes. And one other feature is priority and preemption. Kubernetes didn't have this feature at all in the past. So basically, you couldn't specify importance of your pods. But with priority and preemption, you can do so. In the past, if your cluster was full, and let's say autoscaler was not allowed to add more nodes to the cluster, or you had a cluster which was on-premise, so you couldn't add more nodes to the cluster, and your cluster was full, a new pod, probably an important pod, was created, the pod couldn't be scheduled because Kubernetes didn't have any notion of importance. But with priority, you can provide that. Basically, the higher the priority, the more important your pod will be. Now, if let's say the cluster is full and a new pod, a high priority pod is created, the scheduler looks for pods with lower priority, and if it finds them somewhere in your cluster, it removes those if it can schedule this high priority pod. So it deletes these like low priority pods and schedules the high priority pod. that's pretty much all about the recent developments. I would like to point out the planned features that we are targeting for the scheduler. One is gang scheduling. This is essentially a feature that tells the scheduler either schedule all the pods or none of them. Well, kind of like an expansion of this is to schedule at least the number of pods in a group or none of them. Why is this feature important? So some workloads are designed to provide like sort of interdependency among pods. So basically, pods create input for one another. Some ML workloads are examples of that, or some MapReduce workloads are examples of that. What happens is that if you schedule, instead of all of them, like half of them or a portion of them, they will not progress. So they'll basically get stuck in whatever state they are. And if they're scheduled, they are just using your cluster resources without making any progress. So in those cases, it's better not to schedule any of them. So gang scheduling helps with that. It has a lot of application in batch processing, and as I said, in machine learning as well. We have an incubator project called KubeBatch. Klaus is actually leading that effort. Klaus is the other SIG scheduling lead. He's leading that effort, and we have a proof of concept in KubeBatch. We plan to make it a standard feature in Kubernetes Scheduler. And pod scheduling policies. So in a multi-tenant cluster, some users can put certain scheduling requirements on their pods, preventing other users from scheduling their pods or causing bad scheduling behavior in your cluster. For example, if someone puts a very broad anti-affinity on their pods, let's say anti-affinity to almost any other pod in the cluster, or anti-affinity to any other pod in the same zone, and they get lucky, let's say, that their pods is created first in that zone and is scheduled in that zone, that pod will prevent any other pod in the cluster from getting scheduled there. This is an example of a problem with anti-affinity. There are problems with toleration, for example. We use taints and toleration for different applications. One of them is that you, for example, have expensive resources in your clusters, let's say nodes with GPU or TPU. You go and taint those nodes with, let's say, GPU and TPU taint to prevent pods that don't need those resources from getting scheduled there. But if anybody is allowed to put any kind of tolerations on their pods, then a malicious user or an uninformed user could put those tolerations on their pods, causing pods that don't require those resources to get scheduled on those nodes. So we think we need to have a way to give admin a mechanism to prevent these scenarios. As a result, we are designing pod scheduling policies. These policies, there are a few items here. Those are examples of such policies. For example, you can specify what is the maximum priority in a namespace that users can use, or what kind of tolerations are allowed, or what kind of pod anti-affinity is allowed. We can also enforce some sort of node affinity and anti-affinity. Some users who run security-sensitive applications know that they want to put some of the nodes of the cluster for certain application in the cluster and not share those nodes with any other workload in the cluster. So with pod scheduling policies, you can enforce that all the pods that are created, for example, from such and such namespace, get this particular node affinity, and all other pods cannot be scheduled on these certain number of nodes or group of nodes that are designed or that are dedicated to running security-sensitive applications. Another example, in case that you run a cluster with multiple schedulers, is to enforce one type of a scheduler or one of the schedulers in your cluster to schedule some of the pods created in certain namespaces. There is then the best framework ever, the scheduling framework. So on top of being the best framework ever in the history of mankind, the scheduling framework provides a certain number of features. So it's essentially, it provides a bare bone of scheduling, which includes a scheduling queue and a cache and some event handlers for updating that cache. And then the rest of the features of the scheduler become plugins for the scheduling framework. So essentially, all these filters that we sometimes refer to as predicates and all the priority functions used for scoring nodes, all those become plugins for the scheduler. Also, we add a number of extension points to provide even more flexibility for you to customize the scheduler if you need. We got a lot of feedback from our users that many of them require make sometimes small changes to the scheduler to do things slightly differently, but there was no way of doing it in the past. So the scheduling framework is an effort towards that direction of making Kubernetes, customizing the scheduler easier and maintaining it also easier. So hopefully with this framework, merging new changes from upstream to your customized scheduler will be very easy. It also provides modularity so we can probably debug our schedulers more easily. Another effort, which doesn't have a timeline at the moment at least, is Descheduler. This is another incubator and SIG scheduling. Descheduler responsibility is essentially undoing what the scheduler does. So as clusters run, certain things in the cluster change. For example, we talked about balancing resources in a cluster. So the scheduler can try to balance amount of resource usage in different nodes. But after pods are terminated, those balance will change, right? The balance will change. Or I don't know, maybe at the time that the scheduler was scheduling replicas of a replica set, it couldn't put each replica on a different node because some of the nodes didn't have enough resources. So it had to put multiple of those replicas on a single node. But as time has passed, some other nodes are available. So some of these replicas can be moved to other nodes. So Descheduler essentially tries to remove some of the pods from the cluster that violate some of the scheduling or they are not satisfying all the preferences for scheduling with the hope that they can be moved to better nodes after getting descheduled. As I said, it's already available as an incubator, and it actually kind of works. It's not feature-rich at the moment, but we're hoping that we can add more features and more simulation to it in the near future. And finally, Poseidon. Poseidon is a Firmament-based scheduler. Firmament is a scheduler, came out of a research project in Cambridge. And Poseidon is sort of like a bridge between Kubernetes API to that Firmament engine. It achieves higher scheduling throughput in certain scenarios. So if you have like simple pods in your cluster, basically pods that don't use some of the more sophisticated features of the scheduler, such as affinity and anti-affinity, Firmament can achieve higher scheduling throughput. We haven't tested it very kind of like thoroughly in all scenarios, but the algorithmic latency of Firmament is lower than our standard scheduler. And how much performance improvement we can get end-to-end and in real clusters is still not very well known. But we are hoping that we can achieve better performance at the end with this scheduler for batch and gang scheduling. It's also available as an incubator. If you want to give it a spin, feel free to try it. And with that, we can talk about other questions or comments that you have. Yes. I actually should probably give you the microphone.
Hi. My First question is about some of the limitations of Kubernetes stated in the documentation. It's 5,000 nodes, 100 pods per node,
Yes.
300 containers per node. How much of that is schedulers limitation? Is it?
Good question.
Yeah.
So the scheduler, if you need higher throughputs, I saw you the slides that, for example, right now with default configuration of the scheduler in a 5,000 node cluster, we can achieve about like 50 to 55, almost 55 pods per second, right? So if you want to have, 200 pods per second throughput of the scheduling, and you push your cluster to 5,000 nodes, you will not get it. If you don't care about the scheduling performance, the scheduler is not a bottleneck. So it's basically down to how much throughput do you really need.
And I was just wondering about the pit pressure you were talking about. So like with 100 pods per node, either you have really small nodes or really huge containers with lots of processes. Is that like that 100 pods per node or 300 containers per node is kind of, I don't understand where that assumption comes from. I was wondering if
I don't know either. I'm not an expert about node. I know about the scheduling side, which is this like the 110 is not a requirement or restriction from the scheduler. It's something on a node. We should probably ask that question from the folks in the node. Yes. Do you have an answer to that question or?
Yeah, I think I might have been the origin of that number in many days. I can tell you where it came from. It wasn't super scientific.
Okay.
Yeah, I think I may have been the person who put that number on a piece of paper somewhere. But basically, you have nodes of a certain size, particularly relating to memory usually, and to have useful containers, they usually need a certain amount of memory. And if you take the amount of RAM in typical big servers and the typical sizes of containers, you end up in that sort of around about 100 container or 100 pods range. So I'm sure there are exceptions. There's a SIG Scalability has a document which describes exactly where a lot of these limits are derived from, but I don't think it's got anything to do with scheduling. It's got to do with available resources on typical nodes.
Yeah. Thank you. I guess there's a question over there.
I had a question about pod scheduling policies. I think they're a really great idea. I think they're something that's been lacking for a while, particularly around preventing people that can create pods from creating pods on master nodes.
Right.
If masters are registered as nodes, you can just kind of tolerate the taint and get it there. We actually wrote something to do something like this, to apply scheduling data to pods as they're created. So we target labels, and then we say, if you've got these labels, we actually put affinity or tolerations or anything on them.
Right.
So I think that was really useful. My question is, where are you doing this, and can I mean, our project's great. It's open source. I love it. But it uses initializers, and it's another thing you have to run. So where do you plan on applying pod security policy? Is it actually the scheduler modifying the pod specs after they're created?
That's a good question. So we are still designing this feature, but the latest development on this is that we are going to have two places to enforce these policies. One is at the admission time, and the other one is at runtime, basically dynamically. The reason that the scheduler needs to be involved is that sometimes the node that is eventually chosen for running the pod should be evaluated against those scheduling policies. At the admission time, when a pod is created, it doesn't have a node associated with it. But the scheduler is the only component that eventually picks a node. And after it picks a node for the pod, it can evaluate that node against the policies. And if the node violates those policies, it can go and ask for, it can go and scan for another node in the cluster.
I may be out of date, but as far as I remember, you have like in Kubernetes, there are like two scheduler, one for daemon set and the other one for...
There was.
So it's been converged now?
Yes, there is since 1.12, I think.
Okay.
We
awesome.
have only one scheduler.
Okay, that's
daemon sets are now scheduled. Yeah, but you're right. Daemon sets are now scheduled by the default scheduler. There is one.
You have to tolerate the node status toleration.
Is what?
So if you had a daemon set that you just expected the old scheduler to just
new scheduler node statuses are taints, I believe, and your daemon set has to tolerate those taints.
So yeah, so actually, daemon set controller still creates daemon set pods, and it adds some of those tolerations by default, so that the default scheduler actually takes care of those things.
One follow-up on the daemon set scheduling. I wanted to ask, are daemon sets still broken? Like, I do remember we had some issues with admission for daemon sets. I wanted to know if these were fixed or not. For example, we had some issues with pods not abating to node selectors and stuff like that. I want to know if it was fixed or not.
I am not aware of any broken thing in daemon sets, but maybe. Hi.
I'm maintaining, so
Yes.
I will take the line.
Okay.
Hey, I'm Thomas. I maintain one of the maintainers for the daemon set. So the thing is, when the switch to the new scheduler, well, maybe back to the problem. The problem usually is you have some admission that modifies the pods. And the daemon set controller schedules, well, it now doesn't schedule them entirely, but it chooses the node either way. And it does that before your admission modifies the pod. So if you like change the node selector, it doesn't see that. So the way it used to be, it scheduled the pod to the node anyways, even your admission modified the node selector not to match that node. So kubelet failed that pod, and daemon set has just recreated it, and it was fighting all over. So if you are running like an old version of kube, update.
Okay.
And
basically, you're saying that after we switch to the default scheduler for scheduling daemon set, this problem should go away.
Well, it will stay in pending. So
I see. Yeah.
if you have very restrictive node selector that
Right.
it's added after admission or like during the admission, you can have like thousands put in pending. But at least now it doesn't go into hot loop and doesn't just delete the pod and create it again. Kubelet failed it and it was really bad. Now it basically just have a big queue.
Yeah.
And the purpose solution is not so simple, and we are kind of working on it, but it will be few releases at least. Yeah.
Okay. All right. Thank you.
When you talked about the descheduling helping with node anti-affinity, does that mean if there's
not
a node...
not node anti-affinity.
Oh, I'm sorry, pod anti-affinity.
Pod,
Yeah. Does that imply that if I have anti-affinity to you, you make a scheduling decision, put me on a node, then another scheduling decision would allow you to be on that node, and
No,
descheduling would put me off?
So no, actually, the scheduler never violates those. And if you have required anti-affinity, the scheduler will not ever put two pods that violate that anti-affinity on the same node, for example. But there are certain things can change in the cluster. For example, let's say that you add new labels to your pods after they are scheduled, or you add new labels to some of the nodes in the cluster that are already running some pods. And those labels cause, after all these pods are scheduled, cause the violation of some of the anti-affinity rules. So basically, this is a runtime check. The scheduler does the runtime check. If after addition of those labels, some of these rules are violated, then the scheduler removes those pods. But or sometimes you may have preferred anti-affinity. So preferred anti-affinity may not be satisfied at the time that you're scheduling the pods, right? So, and then later on, the scheduler finds out that there are better opportunities for moving some of these pods around so that those preferences are satisfied, then it removes the pods. All right. Questions? So, okay, you were first.
So I had a question about the scoring changes. So First, did you look at efficiency? Like, efficiency of packing? Like when you toggled how many you were actually scoring? Like, was there actually a, does scoring fewer really meaningfully actually impact how well you end up packing the cluster?
So I believe you're talking about this number of nodes that we are considering. No, we don't. But the scheduler now has a more advanced iterator for nodes. So it tries to basically, instead of just looking in an array of nodes and going from beginning to the end, it goes through like nodes in different failure domains and basically different zones. And it also continues from the point that it basically left off in the previous scheduling cycle. So it tries to satisfy some of these preferences, but of course, when you reduce that percentage to lower values, you may see some compromises in terms of the scheduling preference.
Right. And then the other question is, you mentioned, and I know I've read about it, but I haven't bothered to look at how it does it, the preference to schedule to a pod that already has the image. What does it use to determine that?
What is the use, you said?
Yeah, like what's the heuristic that it uses to determine that the pod already has the image?
So pods are actually, kubelets report the images that exist on the nodes. So the scheduler knows about the existence of those images. It's not heuristic, really.
Gotcha.
Hi. I wanted to ask about a new feature about eviction. You mentioned you have 3 priorities: high, medium, low.
Now, priorities are user definable, so you can add
as many as I want.
Yeah.
Float, integer.
They're integers, but it can be negative minus 2 billion to 2 billion. Hopefully, that's a good enough range for everybody.
That should be okay. Thanks.
This probably isn't necessarily your problem, but I guess something that we frequently run into is when we have, a massive failure nodes or a massive amount of rescheduling in a cluster, it can kind of overwhelm the kubelet and container engine, like trying to put, 50, 60 pods on one node at a time. I guess maybe, again, when I say it, it sounds like this is really a node problem, not a scheduler problem, but I don't know if there's been discussion about who should be responsible for sort of fixing that problem.
So we have actually a feature to limit the number of pods on a particular node. So there is a max pod per node, which can be changed if you want fewer pods on a particular node. But the problem that you're talking about is a little bit more than this. Probably if you, I guess this is actually this should be addressed at different levels, I guess, than the scheduler. But I would like to understand the situation a little bit better that causes this to start, actually. So you see that there are a lot of failures in your clusters because of...
Yeah, like let's say, we have a multi-zone cluster and we have like a stateful application and we use preferred zone anti-affinity.
Right.
And so just so that we're not stuck in a state where we don't have at least a little bit of resiliency for that data, we'll often reschedule into another zone. Like we'll auto-scale a zone to provide the additional capacity and reschedule those pods from like the third zone onto those. And it could be thousands and thousands of pods, right? And like the problem is that it's not that, so like let's say I add 50 new nodes to a zone and I have to schedule 1,000 pods. Like it's not that there's not enough capacity at a steady state, it's that the container engines and the kubelet like really are not very good at starting up a huge number of processes in parallel. And so
this is basically a burst of pods all getting scheduled on a single node, and this is kind of like an oxymoron to scheduling throughput, right? So if you want to improve scheduling throughput, scenarios like this could become more common. I guess this should be addressed at like kubelet side, probably.
Kubelet side.
Or maybe we can somehow rate limit the number of pods creation on a single node.
But I think in the end it's just a battle royale between you and the kubelet team to basically figure out who's going to make this thing not die, right?
Right.
So, all right.
But thanks for the feedback.
Sure.
Probably need
Faster nodes, yeah. So there is one. Sure.
I have a question about the sort of future landscape of schedulers. So there's a couple in incubator right now. Do you see a world where there's a year or two down the line where there's one scheduler to rule them all? Or do you see that there's going to be multiple schedulers in the long term? And in that world, what's the compatibility story going to be like?
Yeah, that's a good question. Actually, from the very beginning, we've tried to make Kubernetes multi-scheduler friendly. And we're going to do that. But the reality is that in a cluster which is under a high churn, multiple schedulers are going to compete against one another. Unless you have very clear partitioning among the nodes or very clear partitioning among the pods, because pods in Kubernetes can have a scheduler name, and you can basically direct them to one scheduler or the other. And then they can also have node affinity, so that, for example, the scheduler knows what group of nodes it wants to schedule them on. If you follow those practices, the possibility of two schedulers competing with one another will reduce. But otherwise, there will be a lot of competition between two schedulers, and sometimes you may see your pods getting rejected by kubelet because two schedulers believe that there are available resources on that node. Both of them schedule their own pods on that node, and one of them gets rejected. So we are going to keep having Kubernetes multiple scheduler friendly, but for standard components, we believe that we should probably go with a single scheduler that supports multiple features.
So for one of the incubator schedulers to get sort of graduated out, would it need full compatibility with the default scheduler's behavior in terms of affinity and all the other things that it supports, or do you see a world where it could graduate out with a known sort of set of limitations?
So those features that we support in the default scheduler are part of Kubernetes API. So definitely any other scheduler that wants to be standard has to support Kubernetes API as well. And yes, there should be compatibility. Sorry if I don't see.
So I'm interested in the kind of memory usage behavior of the core services. And so how does the scheduler memory usage behave with lots of nodes, lots of pods? Because these are scenarios that I haven't tested yet.
Yeah. So of course, especially when the number of nodes grow in a cluster and also the number of pods grow in a cluster, the scheduling memory footprint is going to go up as well. And depending on what features actually you use with your pods, memory footprint could be different. But we have our scalability tests that actually emit some of this data as well. I believe for scheduling like 150,000 pods in a 5,000 node cluster, the scheduler memory footprint could be a few gigabytes. So it's doing a lot of things, and it could be significant.
Well, that still sounds pretty good compared
It's
to this.
still not too bad. Yeah, it's much better than the API server, I believe.
Thank you.
Yeah.
So generally, I have a question about the goal of the scheduler. So sometimes you are trying to optimize for the throughput of the scheduler. In some scenario, maybe we want to be it more. When we schedule the pod, we want it to be more cost efficient. We want to do a better job on bin packing for all the pods.
Right.
And on the other side, maybe on some other case, maybe we want to emphasize more on pod affinity. So how do you balance between the different goals? Because they can conflict with each other.
They don't necessarily conflict all the time. So if we, for example, achieve better algorithmic improvements without really compromising the validity of the result, we can have higher performance without any compromise on the end result, basically. But in some cases, like what you saw, like scoring fewer nodes in the cluster, that can be the case. So when you score fewer nodes in the cluster, the quality of scheduling could be reduced. And some of your preferences essentially may not be satisfied. This is only about preferences. All the requirements of the API will still be satisfied. So in those cases, we have made this configurable for that reason. So you can change the configuration to, let's say, score 100% of the pods so that you can guarantee that you will achieve like the highest quality of scheduling.
So basically, it's still the user needs to be very careful about the configuration of the scheduler, right, to achieve their particular goal.
On a practical level, you said?
I mean, like it should be the user's responsibility. They should be very careful about how to configure their scheduler to achieve their particular goal.
So I believe the default configuration that the scheduler is currently shipped with is pretty good in terms of satisfying almost like 99% of the user requirements. But if someone really wants to emphasize on one aspect of the scheduling and wants to ensure that, I don't know, cost for some reason is very optimized, then they can go and configure the scheduler in the way they like. And actually, the scheduling framework that we are also working on is an effort towards that direction of giving you sort of like all the freedom to customize the scheduler to your needs.
Okay, thank you.
Yeah, sure.
Thank you. I have two questions. One is, do you have any projection about the performance of the scheduling throughput in 18 months, something like Moore's law, like every 16 months the throughput doubles, something like this?
That's a good question. Well, first of all, it's hard to predict, but we have certain goals that we want to achieve. So our goal is to reach 100 pods per second in a 5,000 node cluster. And our hope is that in 1.14, which is going to be released in about 3 months, we are going to achieve that. So 100 pods per second is our goal. But one thing to note here is that the scheduler has a rate limitation for sending bind requests to the API server, right? So let's say that we achieve, I don't know, 1,000 pods per second. We cannot send 1,000 bind requests to the API server. It will overload the API server. In fact, our scalability team looked at this rate limitation and noticed that raising the rate limitation from like 20 pods per second to 50 pods per second causes one whole CPU core basically more usage on the master node. So that's quite sensitive. And while we're trying to improve the scheduler throughput, going further than a certain number is not going to help much because we still need to rate limit the number of binds that we send to the API server.
Okay, I guess you partially answered my second question about the future direction for improving the scheduling throughput, and you cover about the API server limitation, right. And except that, is there any other aspects that we can work on to improve?
You want to answer that question? Okay.
Yeah, as Bobby said, that if you want to improve the whole throughput, actually it's a multi-factor, multi-aspect needs to impact you. So, because every component is pushing stuff to the API server and to ethdcd, and if ethdcd's limit is there, if ethdcd is not improved, what we can improve is on the other aspect. So as far as I know, so right now in Kubernetes, there is already someone, for example, if you know a no heartbeat, so normally in current versions, every 10 seconds, it will try to send a heartbeat to API server. So API server hit HTTP. So you have 5,000, that is, so right, every 10 minutes, every 10 seconds is just give a heartbeat to API server. So, and right now, I think in 1.13 or 1.14, they are improving this signal. It's kind of trying to do a delta or something heartbeats. Kind of regularly, they will send one heartbeat every 1 minute. And it depends on whether they have real information update, then they will send update. And also, I think there is still improvement other fields. For example, if you check out the life cycle of a pod, there are several phases, like create the pod, and the scheduler will try to do the no name binding, right? That also hits the API server, hits the EDC. And also in the Kubernetes side, there are also some intermediate status updated to hit the EDC, hit the API server. So those parts, I think, can also be improved. So it's kind of, yeah, every part can be improved. So right now, I think for scheduler, we will try to achieve 100 parts for 5,000. And for other pieces, they can all improve.
Yeah, basically, the sort of like the short answer to your question is that scalability is a multidimensional problem, and it should be addressed in many different dimensions in order to have a global higher scalability. As you mentioned, and we also mentioned, we will face some issues on the API server if we push the scheduler throughput beyond a certain point. Similarly, we may face other problems with respect to IP routing in our clusters. There were some issues with domain name resolution. If you ran many services in your cluster, there were some issues with a very large number of volumes, dynamic volumes in the cluster. So it's not just something that we can address in one place and say we solved the problem. It's a multi-team effort that we are trying to actually address.
Thank you.
Yeah, sure. Maybe one last question here. Yeah. The switch was at the bottom.
Oh, was it?
Yeah, here.
Jeez, that's really hard to find. What is the plan for anti-affinity where there's more than one, like 2 pods per failure domain instead of, or 2 or 3 or 10 or some percentage instead of like 1, right? Because right now that's all you've got. And there's a ticket on it, but it kind of went nowhere.
Yeah, so I guess Wei could answer that question better. But anyways, we are trying to solve that problem. We were thinking that maybe we can add that feature in the next version. Depending on Wei's availability, we may or may not be able to achieve that. But anyways, it's in our radar, and we are aware of that problem. We actually worked on this problem in the past, but since anti-affinity and generally interpod affinity was 1,000 times slower, we decided at that point we shouldn't add any more features to it until we address the scalability and performance issues there. So now that those are kind of gone, we can think about adding more features, and this is certainly one of those most requested features for interpod affinity, and we're working on it.
Sure. And well, yeah, if you can add that and combine that with the descheduler, then you can get kind of a guaranteed pod distribution where best effort to keep n replicas across domains. So anyway, that's a good feature. Thank you.
Yeah, sure. Absolutely. Yeah. Defend yourself.
Yeah. This is a real problem, because I saw some users says, especially for anti-affinity, because right now the scheduler, the minimum unit is a pod. But think about the rolling update case, right? If a rolling update, existing one is still there, and if you want one to replace that, not just replace, not replace, it's just hold one and try to spin one and to replace that, right? But the new one has no chance to be scheduled to that one. So if we can have this feature, of course, the rolling update issue can be resolved. So right now, what I can comment there is for your deployment, try to use the recreate strategy rather than the rolling strategy. Okay.
Yeah.
First, right?
People are.
I have one more question, maybe.
Quickly, please.
Okay. It's about supporting for serverless kind of framework. Will these serverless be serverless functional kind of operator thing? Functional serverless application be considered as like a workload running supported by the Kubernetes scheduler, or we need some alternative?
What properties does the service need? I mean, we have something called service affinity today in the scheduler, but that's not what you're looking for. I was wondering what aspect of service do you have in mind?
Serverless, sorry. serverless,
Serverless.
functor.
Oh, sorry,
Lambda
I
kind of.
misheard you. Well, serverless is kind of like, I mean, there is nothing particularly different in serverless workloads, really, that requires something new in the scheduler. But definitely, that's the direction that we are going to support. But we don't know what kind of particular scheduling feature it requires.
I think one,
that doesn't exist.
100 like pops per second may not be enough to support this.
The throughput is actually, you're right. Throughput for serverless application is something that is needed. And actually, the reason that we're trying to get to like 100 pods in 5,000 node clusters is exactly to target serverless applications better. But other than throughput, we don't need to add features sort of to the scheduler.